In this video, I introduce a byte-pair encoding for text tokenization. Word and character level models are two extreme text tokenization cases. The word level models require massive vocabulary and fewer on unseen words, while the character level models reduce vocabulary size but learn long-range dependencies. As shown here, this is the original string. We use Z to replace AA to get a reduced string here, and then step by step to get a final reduced string by using X to replace ZY, Y to replace AB, and Z to replace AA. Byte-pair encoding is a data compression algorithm which replaces the most frequent byte pair in a binary file with a new single byte to reduce the file size. BPE starts from individual characters and iteratively merges the most frequent JSON pairs into new tokens. After enough merges, common words become single tokens, while rare words decompose into smaller, meaningful pieces. As shown here, this original corpus. This corpus with frequencies plus the end of a word, and these unique characters in the original corpus. And then we merge JSON pairs step by step to gather a final vocabulary with the token IDs. That will be used as input to the machine learning model. BPE uses the training and the encoding phases to encode the corpus. The training phase reads the entire corpus and learns statistical patterns, and the encoding phase applies the learned pattern to individual strings one at a time. Training phase starts by splitting every word in the corpus into individual characters as shown here. A special end of word marker is appended to each word. The initial vocabulary is a set of all unique characters that appear in the training corpus plus the end of word symbol as shown here. With the corpus represented as character sequences, the training model counts how many times each adjacent pair of token co-occurs. The pair with the highest count wins the first merge. The winning pair is merged into a single token everywhere it appears. The merge row is recorded in the ordered list, which will be replayed later during encoding. As shown here, this pairs frequencies as shown here. First, we choose the most frequent pair, for example, L plus E. We merge them as LE and update the splits here. And then we add this LE into the updated vocabulary. Training model produces the order list of merge rows. Encoding model applies these rows to a character split word. For each word in the input text, for example, as shown here, a BPE splits the word into individual characters, and then iterates through the merge rows in the learned order, as shown here. For example, for the row H plus U, as shown here, BPE scans the current token sequence from left to right and replaces every adjacent occurrence of the pair H plus U with the merged token HU as shown here. The process continues until all rows have been applied, or the token sequence contains only a single token as shown here. BPE encoding is full deterministic, namely, given the same merge rows in the same order, the same input always produces the same token sequence. Because BPE encoding is a deterministic and lossless process, is decoding maps a sequence of token IDs back to text by looking up tokens in a vocabulary and concatenating them. First, retrieval the order list of merge operations created during training. Then convert input token IDs back to their corresponding subwords or character string representations, and then reverse the merge steps in the exactly opposite chronological order of how they were combined, expanding subwords back into the base characters. Finally, concatenate their final decoded characters to restore the exactly original text string without data loss. The BPE method in natural language processing applies the idea in the file compression to the text tokenization, shifting the goal from minimizing file size to controlling vocabulary size, which is better than word level and character level models. For more details, please check with these references. Thank you. Bye.